We're now in position to understand Kirchhoff's laws in terms of the equation of radiative transfer. So let's go back to Kirchhoff's law. So the first law said that a hot solid or a hot dense gas produces a continuum spectrum. The second one, that a hot low density gas produces an emission spectrum. And third, that a continuous source viewed through a cold gas produces an absorption line spectrum. So let's derive first the first law. Let's consider the case when there is no background illumination. So there is only the hot gas emitting. So this case is the optically thick case. If this is the optically thick case, you have a hot dense gas, you have that the intensity is equal to the source function. We're going to see later that in the optically thick case, the source function approaches the Planckian. Actually, you can see that if the intensity is equal to the Planckian, then yeah, the source function is equal to the Planckian. From the equation of radiative transfer, if this is the equation, the I d tau is equal to minus I plus S, and you have the case of black body radiation in equilibrium, that is di is equal to 0 and I is equal to B, then the source function is a Planckian. Let's put the frequencies here to show that the source function is in terms of the frequency. That's the first law, optically thick, and we're going to see later exactly how the source function becomes a Planckian. So that gives you the first law. Let's look at the second law, the emission spectrum. That's the case of optically thin. So in the optically thin case, we already derived what the intensity would be. If you don't have a background illumination, the intensity is the source function times the optical depth. That means that the intensity will be high where the optical depth is high. Since there is no background intensity, these are seen as emission lines. Now let's look at the third law now, which is the absorption case. You have a lamp, which is a case of the first law, a continuum, and then you superpose on that a cold gas, and you should see an absorption line in the same frequencies where in the second law you'd have emission lines. So the third law is the case where you have a background intensity. The background source is a hot gas. Say that there's a hot gas of intensity B. Let's get to the equation of radiative transfer. So in this case here, you can separate between two gases. You have the lamp, which is the background illumination. That's your I naught. That's this term. And you have the cold gas here. Cold gas means that there is no emission. So this term here cancels out, but it gives you an absorption. That's the exponential in here. So you have the lamp that is a Planckian and the absorption. And that is your intensity in the third law. The intensity is a Planck continuum lowered where the optical depth is high, where the opacity is high. Therefore, we're going to see absorption lines. In the next video, let's see the formation of the continuum.